trajectories of a ball in a billiard game, and there are many reasons to study these kind of things that come from physics, but my main motivation is that I think it's a nice and beautiful problem. And so my goal will be to state a theorem about billiard trajectories, and to do that I will introduce some background that is, and hopefully show you what's going on when we do those things. So first, I want to talk about the first character of this story, which is the billiard itself. So I will only consider billiard tables that are polygons. So for example, it can be this or this. And what I want to do is I have a ball and I throw it in some direction, and I want to understand how it behaves. Okay, so it bounces. So since we're not in physics but in mathematics, I assume that there is no friction, meaning that the ball never stops, okay, it continues forever. And, or in this example, it's the same. Okay, we have this kind of trajectories. But maybe the first thing I should do is to explain how we define these trajectories. So we start at a given point, and we go in a direction, with this direction, until we reach a wall, an edge. And then what we do is that we reflect. So what we do is that the angle here will be the same as the angle here. We reflect and we go in a straight line again in the new direction. And we do that over and over and forever. So now I just explained what's happening to the trajectory when we reach a wall, but maybe you have already a question. Have you got a question? Yes?
Will the ball hit the entire surface?
Will it
Will it reach every single point? Is that a question?
I didn't understand the question.
Will the ball eventually reach every single point in the rectangle?
Ah, yeah, that's a question we will address. But maybe a simpler question is that what happens to the trajectory when I go to a corner? Okay? And actually I have no answer to this question, because what we will do is just to consider trajectories that don't touch corners. But you're right, your question is very relevant, and I'm going to talk about it very soon. But first, I introduce just a bit of vocabulary. Okay, my polygon, I will denote it always by what I call an orbit is just the trajectory of the ball. It's a map, it's a function from the positive numbers to p that at time t gives the position of the ball. Of the ball after time t. Okay, this is an orbit or a trajectory, it's the same thing. And it can have different behaviors. For example, it can be periodic. Somehow the simplest thing. So what is a periodic orbit? Somehow the stupid ones, meaning that if I'm in this billiard, I can take a ball and just go up like this, and it will do bing, boom, bing, bing, boom, bing, forever, always the same thing. This is what I call periodic. Does the same thing over forever. Or more formally, there is a time, big T, such that tau of T plus T is equal to tau of T for all. Okay, it should really just mean that. Or another example is, I go this, boom, 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 boom. This kind of butterfly will be another periodic orbit. Okay, so that's a possible behavior of an orbit, and an opposite, kind of opposite behavior is to be dense. To be a dense orbit is basically what you said. It's an orbit that will cover the entire table. So the picture is less pretty. But I have a ball, and I look at its trajectory, and for some reason it will do some complicated stuff and cover everything. So more formally, it means that if I look at a small disk here, the trajectory will eventually enter this disk. If I zoom here, the trajectory will enter. It's for every disk D in P. There is a T such that tau of T is in. Okay? Good. And the question that I want to address is, what your question is, are we always in one of those two cases? Does any is any orbit either periodic or dense? Like, so those two cases are opposites, and I'm asking if there is some intermediate thing. What do you think? What do you think is the answer to this question? No? I would say no also. So the answer is no. There are intermediate things. So, for example, if we are in a L-shaped billiard like this, we can draw some trajectories that do this kind of thing. That will stay in a region. They will like never see what's going on here, but they will never make a loop and come back at their initial state. So there are some intermediate behavior sometimes. But my goal is to present a result which says that if the polygon is nice enough, then actually this never happens. So my goal is that sometimes, yes, sometimes the answer is yes. Okay. And to do that, I will introduce a trick that is used to study these trajectories. The trick is that from a billiard, we will construct a surface, and the trajectory will be studied in the surface. Do you have questions? Okay, so the second character of this story is the surface. The surface. Okay, so first I will define what kind of surface I want. The surface I want are called translation surfaces. translation surface, it's a polygon with sides glued. So the edges are glued by translations. Because it's not understandable maybe like this, but on the picture you will understand it. So for example, I can take this polygon, which is the simplest one, rectangle, and glue this side to this side. When I mean by a translation, it's just that this side here, I can just move it by a translation to this one. And I also glue this one to this one by just moving. That's a so what does it look like if I glue top and bottom? I take this thing and glue them. I get a cylinder like that. Agree? And now if I want to glue left and right, I have to take my cylinder and glue it. It gives me a donut, which is also called the torus. So that's an example. And another one, more complicated, is I take a regular octagon, so it's just the stop sign, and I glue the top to the bottom, and this one I translate it here, this one I translate it here, and this one here. And that, you can do the same kind of reasoning. It's a bit harder, but you can convince yourself that you get something that looks like that. Okay, so that's a translation surface. And sometimes I want to say that two translation surfaces are the same, even. So I would say that they are equivalent. If they satisfy something. So I would say that two translation surfaces are equivalent if they differ by cut and glue. So again, I will show you what that means on the picture. Say I start with this polygon, where I identify this side with this side and this side with this side. It's a translation surface. What I can do is that I can take my scissors and cut along this line. Because when I cut, I will have two triangles. Okay. Two triangles where this side must be glued to this side. And what I can do now is that since this side is glued to this side, they have the same marking, I can move this one here, and glue them back to get this surface. Okay, so these two surfaces, I said that they are equivalent because they differ by this cut and glue operation. Okay, so why am I talking about those things? It's because it's very useful for billiards. Because of the following trick. So there is a trick to study billiard trajectories. say I'm studying a trajectory in this billiard. So I'm throwing a ball. It's nice, it's easy to understand, but then I hit a wall and it becomes complicated because I change my direction. And so the trick is, instead of reflecting the direction, I will reflect the billiard. Okay? And so I will create a fake billiard up there that is a reflection of this one, so that my trajectory continues in a straight line in this reflected billiard. Okay? And continues, and here again I should reflect my trajectory, but instead I want to reflect the billiard. And the thing is that if I reflect the billiard once and again, it's the same thing as, I mean, the billiard I will get here is a translation of the billiard I have here. So instead of having a new billiard, I will glue this side to this side. Okay, so you see we're coming to this thing. And so my trajectory continues here in a straight line, and it hits here. Again, I will reflect the billiard. Oops. That it continues in a straight line, and again I reflect the billiard. And when it hits here, I could reflect one more, but it will be the same as this one. So I just do this, and my trajectory continues like that. And here I can reflect like that, but it will be the same as here. So I continue. Okay, and I have created a new surface. If I forget what's inside it, which is a translation surface in which I'm studying a straight line. Okay? So from my polygon, I create a translation surface. And the trajectory of the billiard is a straight line. So it's simple. I'm just going to give you I'm going to draw another example of this trick. Another example is if I play billiard in this L-shaped thing. Again, I do the same thing. If I have a trajectory like that, instead of reflecting, I reflect the billiard. And if I go here, I can reflect it, but again, I will have the same, I will have this L translated, so I will rather glue this side to this side, and this side to this side. And if I have a trajectory going here, I want to reflect the billiard here. And maybe I will create the last copy of the billiard, so that whenever I go in a direction, actually, I can just understand by translation. Okay, so from the L-shaped billiard, I create this surface that is the flag of Switzerland, where I drew that in an appropriate way. Okay, so this is a translation surface associated with this billiard. And we do that in general. Just there is a technical issue with this trick, but I don't care so much, just to not lie to you, is that it works if the angle of the billiard are rational in degrees. Otherwise, I will have an infinite number of copies and it will. So now we assume that the angle of P are rational numbers. Okay. So have you got a question on this trick? Okay, so now I have associated to a billiard surface, and I want now to understand. I mean, the theorem I want to state is that when this surface is symmetric, everything is fine. And so I want to measure how symmetric it is. And for that, I will introduce something that is called a group. So it's the third character of my story. Do you know, are you familiar with matrices?
Yes.
You are? Good. We won't look at complicated matrices, just with 4 numbers. It's the only one I know. So, a matrix, for me, is a 2x2 matrix. It's ABCD. And you know maybe that this quantity is very important. AB minus BC, it's called the determinant. And I will require this to be 1. Okay? And I will denote by SL2. It's all the matrices AB minus BC. And that's the notation. That's all the matrices that are these places. Maybe you know that if you have a matrix like that, A, you can see it as a function from R2 to R2. It's the function xy maps to ax plus by cx plus by. Okay. And what I want to say is that, okay, so for example, my favorite example is this one, 1, 1, 1, 0, AD minus BC is 1. And so this is the map xy maps to x plus y and y. So what I want to say is that if I have a matrix and I have a translation surface S, I get a new translation surface. Let me explain that. Okay, so I will explain on an example, as always. So say I have the simplest translation surface, which is a square. So it's 0, 0, 1, 0, 0, 1, 1, 1. Okay, this is the translation surface. And I also have a matrix, which is my favorite one, 1, 1, 1, 0. And I want to say that I get a new translation surface, and what I will do is look at this polygon, look at its image by this. So, where is the point 0, 0 sent by this symbol? 0, 0? Yes? Where is the point 1, 0 sent by this? Okay? Good. And actually it will preserve all these segments, so all these segments will be sent to this segment. And where is the point 0, 1 sent? 1, 1. Okay, so this guy here. And 1, 1? 2, 1. Yeah. Okay. And so actually all these segments will be sent to this segment. And this segment will be sent to this segment. Okay? And so my polygon is sent to a new polygon, and my translation surface has changed. Okay? Maybe I can draw another example. If I take this matrix, this is again in SL2 because AD minus BC is 1. Do you see what shape it has, the image? At this point, where is it set? Yes. Good answer. So this is 1, 0, 1. This is 0, 1 half. And the image will be this thing. This is 0, and this is 2. Okay. So is it clear? I have a translation surface, I act by a matrix, and I have a new one. Okay. Now, I want to define something that will encode how symmetric is my surface, and that is the Veach group. So the Veach group of my surface S is V of S. It's all the matrices such that when I transform S by this matrix, I can cut and glue this thing to get back this. Okay? So that's a measure of how symmetric is my surface. Okay, maybe just on this example, if this is S, this is A. Here I have AS, and I have explained earlier that when I cut here, I can glue it back to get S. So this matrix is in the Veach group. However, this matrix here gives me this surface, and there is no way of cutting and gluing it so that we get back this one. So this matrix is not. And okay. And the thing that I want to communicate is that Vs is big. So we have a lot of matrix in this thing. It's the same thing as to say that S is very symmetric. Because when you have a surface that has a lot of symmetries, if you move it by some matrix, you have some chance that you can cut and glue it back. If it's twisted, you have no chance. Okay. So this is measuring how much the surface is symmetric. Okay. So let me do a small recap of what I said. Recap. We started with a polygon. We wanted to understand its trajectory. And what we did is to use a trick to get a surface. Okay. And this surface we want to measure how symmetric it is. And for that we introduce a group, so a bunch of matrices that is the big group. And now I just want to quantify and to say when this thing is big, so when my matrix is symmetric. So this is the last thing I introduced. It's a bit of geometry that will help us telling when this bag full of matrices is big or not. Okay, and so I want to introduce briefly something that is very deep and interesting and fascinating, which is called hyperbolic geometry. And it's a geometry that is different from the one you know. It's a geometry that takes place in this disk. This is the disk. It's called sometimes the polygonal disk. And since I'm French, I have to say it in French. Disk. And okay, so everything takes place here. We have some lines. So how does it go? Suppose you are living in this disk. If you're in the middle, it looks like usual geometry. Everything looks very normal. But the thing is that as soon as you walk towards a boundary, here, it will get colder and colder. And you will have a very difficult time moving because it's too cold, your muscles just don't move, okay? So maybe if you are living here and your best friend is living there, if you want to go and visit him or her, it's not very smart to go this direction because it's too cold, you're too close to the boundary. Maybe it's smarter to go a bit closer to the center where it's warmer and then go back. And so this will be the straight lines, the shortest path of our geometry. Okay? And I won't say much about this geometry. I just want to say that SL2, the 2x2 matrices, they are the transformations of this disk that preserves this weird distance, that preserves the distance. Okay, so it means that if I have a point here, Z, and I have a matrix A in SL2, I get another point. It transforms my point on the disk. Okay, so why do I talk about this? Because it will help me quantify being big in SL2. So now let me take a bunch of matrices, gamma 1, gamma 2, in SL2 of R. Okay, and I want to define what it is for gamma to be big. So as I was saying, if you have a point and a matrix, you get a new point. But if you have a point close by, it will give you a point close by. So if you have a little region D, AD will be another little region. Okay. So now I claim the following. That for gamma, there is a region d gamma in my disk such that when I look at gamma 1 d gamma, gamma 2 d gamma, etc., it times the disk. I will explain that with a picture. So I have a bunch of transformation, and I say that there exists a region d gamma such that when I apply the transformation, I get another region, and when I apply another transformation, another region. Okay, gamma 1 d gamma, d gamma. And tiling means that it will fill the entire plane without overlapping. So means that overlapping. And to measure how big is gamma, what I say is that I look at the size of the gamma. And gamma is big is the same as gamma is small. Because when gamma is big, I have more tiles. So I can have smaller tiles. Yes?
Is that gamma like an infinite set or is it a finite set?
Yes. So it is an infinite set. I mean, it can be finite. Yeah. Here I suppose that it's infinite. But actually, it can be finite. But if it's finite, the gamma will be very big. It will be almost everything. It can be both. Okay. So my definition is that gamma is a lattice if the area of the gamma is finite. So, okay, when the gamma is small, so it means that gamma is big. Lattice means big. Okay. If you were lost in this part, just remember that I define what it is to be big for this set of matrices. Now I can finally state the result I wanted to state. So it's a theorem due to Beach from 1989 that tells you that so the behaviour of the surface associated with a polygon is a lattice, which really means that the surface is symmetric. So if you have that, then every orbit, every trajectory is either dense or periodic. So we have a nice dichotomy, and it's called actually the Beach dichotomy. And I will just finish with corollary. So a consequence of that is that this applies in particular if you play billiards in those simple shapes. So if you have like, how do we say, triangle with, what do you say? I don't know the English word, sorry. Okay. If you play billiard in a square, or if you play billiard in a regular pentagon or regular hexagon, and so on. In all regular polygons, if you play billiard, you have that every trajectory will be dense or very. And I will finish with this. Thank you.